Okay, this little tutorial is to walk you through the differences between light and electron microscopy. So light microscopy is what we've been doing. We're basically just using a light source. It usually goes through the specimen, and we use a series of lenses to magnify that to produce an image that's much larger. An electron microscope essentially works the same way, but the main difference is it uses a beam of electrons, and it can see things that are a lot smaller, and it can essentially produce an image with a lot more detail of structures that are a lot smaller. So before we can really compare the two and get into that, we really need to go over a few key terms. So firstly, magnification. So magnification is just how many times bigger something appears. So when we look at something under low power or medium power or go on to high power, each time it appears bigger, and the number of times bigger it is, that's basically the magnification. So here's a formula for magnification. Now I don't think you really need to remember this. I think it's pretty intuitive actually. So magnification is the size of the image, the size it appears under the microscope, divided by the actual size. And that makes sense. If you think about it, we can rearrange this formula a little bit. If we take the actual size times the magnification, that's how big it appears to me. So the actual size under medium, sort of under the medium power, would be the actual size times 100 times is how big I'm actually seeing it. And I can work backwards. If I measure the size of my image, or if it looks a certain size, divided by the magnification is how big it actually is. So I think that's fairly obvious that one. You can either learn the formula, but I think, to be honest, you could work that out. You know, if I'm looking at something under the microscope at 100 times magnification, obviously the real life object is going to be 100 times smaller, so I could divide by 100 to find out how big it actually is. Alright, so just to clarify the term, we've got some images here just to illustrate it. So this is no magnification, 3 times magnification, things look a bit bigger, 8 times magnification looks bigger still, 20 times magnification, even bigger still. You might be wondering why we got dots there. Well, it ties in with our next term. Alright, so just before we move on, the eyepiece is 10 times magnification, the objectives, the low is 4 times, medium 10 times, high is 40 times. And the low power objective is the shorter one, and the high power is the longer one, but they've usually got those values stamped on them too. To work out the total magnification, this should be easy stuff, you've probably done it as juniors. The total magnification is the eyepiece times the objective. So if we're on the medium objective, for instance, it's 10 times the eyepiece, which is another 10 times, so 10 times 10. The total magnification is going to be 100. So when you're dealing with magnifications, it's essentially always multiplying or dividing. We never sort of add or subtract. It's always a factor, so it's always times by 10 or divided by 10, or etc. Cool. Resolution. So this is why we were looking at the dots. Resolution is another term that's really important when we're talking about microscopes. And an electron microscope essentially can produce a much higher resolution image. And or rather, it can resolve things that are much smaller. And that's really the key difference. In theory, with a light microscope with lenses, you can if you have enough lenses or the right shaped lenses, you can magnify things as big as you like. But the problem is that at some point the image just is too unclear. It's too fuzzy. It's not sharp enough. You can't actually make out any detail. So at some point, simply magnifying something doesn't help. You have to improve the resolution. So resolution is the ability to distinguish between two separate points. And it's quite a specific definition, and this is one you probably do need to learn. But resolution is essentially how sharp or clear, or how much detail you can make out in the image. So you've probably have heard people talk about a high-res image. A high-resolution image is one that has a large number of megapixels, which essentially means it's mega, as in millions of, pixels are the little dots that the images are made out of. So think of it like this: if I were to try and draw you, or paint or something like that, if I tried to draw you using 100 million dots, 100 megapixels, I'm going to get a lot better quality image than if I try to draw you with 100 pixels, just 100 dots. With 100 megapixels, so 100 million dots, we're probably going to be able to make out each individual eye and the ears and all those different parts. Whereas if I try to draw you with just 100 dots, we'd be lucky if we can make out your outline. So it's the ability there to distinguish between 2 points. Using more dots means we can see features as separate, like separate eyes and ears and all those little points. Whereas with a low resolution image, we can't make out those differences. It kind of blurs together. So to illustrate that, I've got some images here again. Low resolution. Here you can see those black dots on the board essentially blend into each other. We can't see them as distinct separate points. Whereas a high resolution image, okay, we can see there clearly that they are 2 separate dots. They're distinct points. And that's really the difference. So, why is it that an electron microscope can achieve a high resolution? Well, basically, it's got to do with the wavelength of light and electrons. So the wavelength of light is usually between 400 nanometers and 670 nanometers. The 400 being the violet end of the spectrum, and the 670 sort of being the red end of that spectrum. Now, exact values on there, well, it depends also on what animal you're looking at. Some animals can actually see further towards the edges of that spectrum, and it even changes a little bit with age, I believe. So, those values are a little bit give or take. They're approximate. But in theory, this means that we could actually, because violet has a shorter wavelength, you can see that the wave there is smaller in size. We're going to be able to see slightly smaller or get slightly greater resolution with violet light in theory, although it probably doesn't make a huge difference. Electrons, when you have an electron beam, they have a much shorter wavelength. And that enables you to see things of an even smaller size, and we'll explain why a little bit in a minute. But firstly, electrons you probably think of them as particles, but they're quite interesting in that respect. That a beam of electrons can be considered as a beam of particles, or a beam of electromagnetic radiation with a wavelength, and electrons happen to have a very short wavelength. And actually it depends on the energy. If the electrons are high energy, then I believe they have a shorter wavelength, so it can even be adjusted. But a much shorter wavelength than physical light. This video clip I'm going to play is just to give you an idea of what we actually mean by a nanometer.
Hey, do you know what nano means? It means small, very small. It is 1,000,000 times smaller than the smallest measure on a ruler. If you want to get an idea of how small a nanometer really is, you'll need to take a piece of hair from your head. Go on, it won't hurt. Got it. Now take a good close look at that strand of hair. Not much to look at, is it? If we were to shrink you down, smaller than the smallest thing you can see with the naked eye, you will find that your piece of hair starts to look a lot more interesting. You are now about the size of a red blood cell. Your strand of hair is a massive tree compared to you. Even at this size, you're still about 1,000 times too big to be considered nano. To get you down to the nanoscale, we will have to shrink you to about 100 nanometers tall. Hey, where are all the lights? You are now smaller than the wavelength of visible light. You are practically invisible. But for the sake of demonstration, I think we should turn on some lights. At this size, the red blood cell is 1,000 times bigger than you are. It is like an enormous stadium. Welcome to the nanoscale. You could probably hold a common cold virus in your hands quite comfortably now. The rhinovirus is only about 30 nanometers across, and is nearly impossible to see next to the red blood cell. A red blood cell is too big to be considered nano. However, it's made up of all kinds of nanomaterials. If you were to look close enough, you would see that the outer walls of the cell are stabilized by a flexible, mesh-like protein skeleton. The bars and connectors that make up this mesh are considered part of a nanomaterial. Without these reinforcing nanostructures, the cell would be much more fragile and not nearly as flexible. It wouldn't stand a chance in your body. Everything is made up of nanomaterials. Nanomaterials are an arrangement of molecules and atoms that, when combined, create stable building blocks that can be made into larger, more complex materials and structures. Which is pretty much everything, including this little piece of hair. I bet you didn't think there was so much going on in such a small amount of space.
Cool. Okay, so the wavelength of visible light, so down the violet end of the spectrum, is 400 nanometers. And as a general rule, using electromagnetic radiation of any sort, you can see things at a distance that is half that of the wavelength. So the resolution, the ability to see things that are that distance apart, is usually half the wavelength. So essentially, for example here, visible light, wavelength of 400 nanometers, we're going to be able to see structures that are maybe 200 nanometers is the limit. So anything smaller than 200 nanometers, we're not going to be able to see as separate from its surroundings. So anything smaller than 200 nanometers, we're not going to be able to see with a light microscope. So in this diagram, sort of the mitochondria, you can see there we're probably still going to be able to see that. It's 1,000 nanometers, so it's down the bottom end. It's going to be tricky to see that, and the microscopes that we use at school, you probably won't see mitochondria. But with a light microscope, it is in theory possible to see mitochondria. However, if you look at these black little dots, these ribosomes, they're only 22 nanometers, so they're actually a lot smaller than the wavelength of the light that's actually passing by them, and that makes them impossible to actually see, or to see as separate, distinct from their neighboring surrounding points. So that they're just going to appear as blur into their surroundings. So free electrons behave like electromagnetic radiation, and when a metal is heated sufficiently, some of its electrons gain so much energy that they can escape their orbits, and they have a very short wavelength. So a beam of electrons or electrons have a very short wavelength, about 2 to 12 picometers. So that's 1,000 times smaller again than nano, and so the greater the energy of the electrons, the smaller it is. So that's what determines whether they're down at the 2 picometers or up at the 12 picometer end. Although in both cases, we're looking at a wavelength that's so short, we're going to be able to see structures that are very, very small. So that's how an electron microscope can produce images with a much greater resolution, or resolve, which means to be able to see as distinct. It can resolve structures that are so much smaller. There are actually two types of electron microscopes. The first is a scanning electron microscope, and so what you see here is a scanning electron micrograph. So that's something a student asked me about the other day. What's the deal with when we say that, like an electron micrograph? Well, think about it. It's just like photograph. So this is an electron micrograph, is a picture taken using, instead of photo light, it's using electrons, all right, as the radiation source to capture that. So an electron micrograph is the picture that's produced. An electron microscope is what you're using to produce that image. So a scanning electron microscope essentially basically fires a beam of electrons, and then they're reflected off the surface. So this is used to look at things that are too thick, where the electrons wouldn't be able to pass all the way through. So you can see this lovely image of an ant's head. Electrons have been fired at it. They bounce or reflect off the surfaces there, and that can be analyzed to produce an image. So we essentially see how the electrons have bounced off, how they've been reflected, in order to produce this image. The other one is a transmission electron microscope, and that's more like the light microscope in terms of the fact that here we have electrons going through the specimen, and so some areas that are thicker or more dense, the electrons are not going to get all the way through, whereas in the thinner areas, or where it's just water, where it's less dense, you can have more electrons passing through the sample. So it's essentially sort of sampling density, or essentially what's retarding those electrons from getting through the specimen. So this is like the light microscopy, and what you really get here is more sort of a 2D image of what really appears to be almost like a slice through the specimen. The image here is actually of the centrioles, and so you can see the centrioles are a very small structure within the cell, and here you can really make out those the tubular-like structure and that organization of those proteins into those tubes that make up the centrioles. So we can see structures that are very small with this, and that's how we see all those organelles, especially things, the smaller ones like ribosomes and the centrioles. Okay, finally, I've just put up here a few things about size. So the average plant cell is between 30 and 100 micrometers. An animal cell is between 10 and 100 micrometers. The nucleus of a cell is about 6 micrometers, but that can vary quite considerably. A chloroplast is about 5 micrometers. Mitochondria are about half to 1 micrometer, but again can vary by a reasonable amount. The Golgi is about 2 micrometers. But it's only that's the length along the longest sort of axis, but it's only about 10 nanometers wide in a lot of cases, maybe sometimes a little bit more, but that's below that value, so it is getting very difficult to see. Vesicles are about 100 nanometers, so they're definitely below that cutoff. Ribosomes 22. Membranes, that's probably one that you really need to know. Membranes are about 7 nanometers thick. So the cutoff is 200 nanometers with regular visible light. Under a light microscope, you cannot physically see anything under 200 nanometers under a light microscope. And let alone with the ones that we have in school, like a fairly basic light microscope. So membranes, you're never going to be able to see a membrane. And so for some of the organelles, if the interior and the exterior look fairly identical, or there's no difference in density, if you can't see the membrane, well, then you're not going to see the organelle either. So that cutoff, the two values to remember there is the cutoff, 200 nanometers, anything under that, it's going to be impossible to see it, and probably the membrane one. That membranes are 7 nanometers, so they're definitely going to be impossible to see under a light microscope. However, using an electron microscope, we can see all of these things easily. So we've got a wavelength of 2 to 12 picometers, so even at 12 picometers, in theory you can reach a resolution of 6 picometers, which is 1,000 times smaller than even the membrane. So we can definitely make out even the smallest of these structures in the cell. Cool, that's it.